So my name is Ben Miller. I work at Dragos as a threat operations center, so I'm a vendor. However, a lot of the discussion over yesterday and today certainly focused on information sharing as well as automation. My background prior to being at Dragos is information sharing. So I worked at NERC with the electricity ISAC for almost 6 years. And then prior to that, I was at Constellation Energy, which is technically now owned by Exxon Energy, but they also serve the local utility here, Baltimore Gas and Electric. So I've tweaked my slides a bit after seeing some of the keynotes and the discussions yesterday, because I have opinions on some of this and how it relates to industrial. So Dragos itself is a software company that focuses entirely, we don't do necessarily like siloed automation or information sharing, but instead industrial control system security. So from an industrial control system security perspective, we kind of, our defining moment in the community was probably in 2010, where we talked about Stuxnet. And then in 2011, we continued to talk about Stuxnet. In 2012, we talked about Stuxnet. We started changing that narrative over time because we have had new things going on. So there's some discussion on Ukraine, 2015 or 2016, as well as more recently Trisis, which I'll talk to a bit shortly, but impacted safety systems within a DCS, a refinery out in the Middle East. The challenge in the state of security on the industrial side is much different than a lot of the discussions that we've had over the last 2 days. So I think, I think we have a lot of challenges inside of ICS. None of them are insurmountable by any means, but we have a talent gap. So from an industrial control systems perspective, we have either process control engineers that are very good at industrial control systems, or we may have cybersecurity staff that have no idea of industrial control systems. And over the last 10 years or so, we've started building up, so there is some of the fusion between those two skill sets. The challenge is, up until now, all of that has been focused on creating good architectures for industrial control systems, redesigning them so that they're more resilient and capable from a security perspective. There's not a lot out there people-wise that actually know how to defend industrial control systems networks. How do you actively protect and monitor and respond to intrusions inside of industrial control systems that is a challenge. And then I think it was yesterday, Harley mentioned on one of his slides, there is a slide, I forget the exact language, the assumption that there's a lot of tools, there's a big ecosystem. That's not really the case inside of industrial control systems networks. So there is not a large ecosystem. I think Richard's keynote earlier today also talked about 150, or the banks had like 300 tools and they're trying to get it down to 150 tools. That's not really the problem inside of industrial control systems. That's changing. There's now an ecosystem of tools. Dragos is one of them that's focused on creating visibility in those environments. But we're very much at a nascent state when it comes into creating visibility into control systems, which is kind of a prerequisite for both orchestration as well as information sharing. And then finally, threats. In 2010, we talked about Stuxnet for a good 4 or 5 years because it was the only anecdote we had. The threat landscape was largely unknown. We could not characterize it beyond that. And certainly that's changed. Well, we're no longer just talking about Stuxnet. We have a lot of other use cases, as I mentioned. But they're anecdotes that you can count on your fingers. So that's not helpful from a defender's perspective in any means. Now, I didn't want to assume, how many folks have had some exposure to industrial control systems over the years? So about half. So this is a common construct called the Perdue Model from Purdue University on a way to think of how industrial processes work and all the equipment thereof. Starting down at the level 0 where you have your field devices, your final control equipment, which is ultimately the actuators, the sensors that are controlling the industrial process. And those may be dumb. They're becoming more intelligent. They're getting processors on them. However, they're still pretty dumb. And then the next level up, controllers, right? So these are PLCs, these are RTUs and other devices out there that are directly wired to these field devices and taking actions using logic on those controllers to do whatever is needed. And so if it's above temperature, above pressure, an action is performed based on that controller to change that status or maybe just monitor that status. And then level 2 is really where you start getting into more friendly environments from an IT perspective. You'll start seeing Windows boxes. You'll see servers. This is where the system operator is in the loop. So yeah, yesterday there was a lot of talk about information and automation without anybody in the loop. The primary focus in a lot of industrial control systems, especially the really important processes, are having a human in the loop. So it sounds very scary to me when we're talking about making changes in the environment and in industrial control systems, say firewall changes or blocking of processes, without a human in the loop, because the entire system, the entire mission is based on having a human in the loop. But that human is operating at that supervisory network. So these are the energy management systems, the SCADA systems that are deployed out there. And then level 3 is the operations and support functions. So this is where the engineers help program the PLCs. This may be where your patching server is, your domain controllers, your other auxiliary IT systems. And then you move further up the stack to the enterprise, and then you can say level 6 would be the internet or third parties. So with that, the state of the art for attacks is Xenotime. Well, what Dragos calls Xenotime. Xenotime is what we call an activity group. So Dragos does not do attribution. There's some discussions on that yesterday. What we do is define activity groups. Activity groups being a term of art from a type of intrusion analysis called the Diamond model. It's a white paper that you can look up online. But basically, it's a clustering of data based on intrusions. So you have one intrusion, you have two intrusions. When there's a lot of similarity between those intrusions, it makes an intrusion set. And then from an intrusion set makes a campaign. And then when you have a series of campaigns, you can draw that circle around those series and say this is a activity group. So Xenotime is an activity group that we've associated with a piece of malware called Trisis, that we call Trisis, also known as Triton. Trisis is the first ever malware that's specifically targeting, in our viewpoint, specifically targeting actually impacting human life. So when I talked about those controllers at that layer 2 aspect, level 2, there was another system that's another set of controllers for high priority events. So these are called safety systems. They're there to act as a final check on if the controllers are doing the right things within that facility. So if there's an overpressurization event, or if fast rotating equipment is doing something it shouldn't, it's a safety systems function to safely turn off the plant, the refinery, the equipment into a safe state to protect human life and the facility itself. Trisis specifically went after that safety system. There's a Schneider electric tool or controller called Triconics. This is basically a PLC, but it's made for safety systems. It has 3 CPUs running the same program file, and then that goes through a vote. So if one of the CPUs disagrees, the other 2 CPUs win the day and perform that action or don't perform that action based on the logic. Trisys is essentially a rootkit. A memory resident rootkit within the Triconics controllers that was uploaded there. It was a program that's basically just a PowerPC binary, because the Triconics was using PowerPC CPUs that removed itself from the process list and kept running, and where another component on the network could send a command to the Trisys, and then Trisys would perform that action. It's memory resident, so when you turn off the device, like say if you're performing diagnostics on this particular controller, Trisys itself vanishes, which makes it really challenging from a forensics perspective of how do you get in front of that? How do you detect that? How do you defend against that? How do you, if you do find it, perform forensics on that? Because it's not a Windows box. There's not a command line. You're interfacing with an embedded device, right? So I talked about the classic Purdue model. This is probably more likely the model that you would see in a lot of the world, where, and I'm being kind of generous, level 0 is probably also level 1 through 3. But basically, you have a large contingent of devices that are not segmented off in any fashion. You have vendors who were actively selling, integrators who are actively selling the SIS, the safety information systems within the normal DCS. Ideally, they should be completely segmented off from the controllers. That's the entire purpose, is having another process loop outside of the main process loop, understanding what's going on in case, and being independent to take an action if designed. However, that's very expensive. So the integrators were actively integrating the SIS with the other controllers. Some controllers are doing both process and safety control on the same device, for instance. They're being networked onto the same LANs and other equipment, so they can be accessed by the same engineering workstation and reduce costs. It's absolutely there to reduce costs, but the challenge is that the security model itself is just a model, and it's not anywhere close to reality at a lot of these facilities. Not all of these facilities, a lot of these facilities. The big circle there, I would arbitrarily call that like the level of visibility within a typical environment. So we have great visibility within the enterprise and on the business networks, IT systems. That drastically changes when you move down the stack. You may have some perimeter security with firewalls. In a lot of the environments, that's where it stops. There's not a lot of sensing on the networks themselves, not a lot on the hosts themselves, which is very challenging from a lot of the asset owners have challenges on even if they want to deploy new tools on these devices, they have support contracts that prohibit them from doing that without breaking their warranty and their support contracts with these large vendors. So it's not out of not out of a lack of desire, but on a very challenging kind of ecosystem supply chain problem. There is one dot right there for the field devices. The connections historically between field devices and the controllers are serial connections. So they are not networked. They're becoming more networked, but ultimately, if you're only relying on network visibility, you're not going to get all the way down the stack here. So the world's kind of changed a lot. There's when you're in ICS, there's OT-IT divide. There's convergence of converging IT and OT, and a lot of talk over the last 15 years or so. I see someone smiling. I always avoided those conversations because it's a real problem. The OT team has definite opinions about the IT team and vice versa. And that's because of the mission. OT's mission is entirely different from IT. There is a lot of consternation between the teams, a lot of trust that's been lost because they didn't understand each other's mission. The challenge is that the attackers, the adversaries out there have already converged. They've already converged their IT and their OT, which is evidenced in Trisis, as well as Crash Override, which piece of malware that led to the Ukraine 2016 transmission substation outage. The convergence on the attacker side has already happened. They're actively understanding how to, the approach of infiltrating these devices, these environments, and having a specific outcome that they're looking for. This is always the case where the defenders are catching up, but now there's a lot more complexity where the defenders don't even necessarily like each other. And we're talking yesterday about working closely with our competitors. It's really challenging when our competitors are in the same organization as us. So if you can't share and collaborate internally within your company, how can you reach out into the broader community? We're getting better at it, but we have quite a bit ways to go. So moving from understanding this current state of environments that are really not well architected for security. They don't have good visibility. We have attackers out there that are doing attacker things and infiltrating these environments and causing real life impact. Where do we stand on how do we respond to all this? How can we do good things? I'll refer to NIST Special Publication 800-82, which is focused on industrial control systems, and to hammer home the point of just the state of where we are in industrial response. This is a great special publication. NIST does great work. I think I want to say it's like 600 pages focused on primary architecture. How many pages do you think is focused on incident response? How many? Five? It is almost 2 pages on incident response. One of those pages is a call-out section on industrials, ICS-specific detection, I think. And it's not really ICS-specific. I want to say it covers denial of service and some other leading indicators that are just as applicable inside of IT. So this is a challenge. So let's instead refer back to NIST 861, which is focused on information handling on just the IT space. And maybe we can take some good lessons from there. I like their definition of incident response. It helps ground us. So what am I talking about? We're talking about systematically responding to events, making sure the appropriate actions are taken, minimizing the impact caused by the incidents, and then circling that back into a feedback loop on applying lessons on how they get handled in the future. Sounds good. The table of contents, there's one large section called detection and analysis, and these are the subsections: attack vectors, signs of an incident, sources of precursors to the and indications, and then incident analysis. And then there's also 3 others that are more like incident response planning, incident response plan. So I'm not going to really talk about those and kind of focus on that first 4. The challenge, this is pretty straightforward on the IT side, but the challenge on the industrial control system side is you don't even know what's in the environment. So how can you defend it? You have zero visibility on what's actually deployed in there. What's talking to what are the the likely attack vectors, what other networks are you attached to? It becomes, if you can't answer those questions, it becomes very challenging to be able to respond in any sort of meaningful way. And I already talked about the threat landscape. We're not defending about Stuxnet, or at least I don't think anyone in this room is defending us against Stuxnet. However, there's a lot of concern on capabilities like crash override, Trisis that are out there. Those are like two anecdotes. So what else is there? And then going back to that talent gap of training the defenders out there in order to be able to understand what signs for an incident are, or what the precursors and indications, what are the ramifications impact from that, are all challenges. And these can be applied to the Purdue model. So each of those questions, what are the attack vectors, what are the signs of an incident, what are the precursors and indications, and how do I do incident analysis? Each of those questions need to be broken down based on each of those layers of the Purdue model. Because each of those layers of the Purdue model, whether they're structured 0 through 3, or they are 0 through 3, the infrastructure there dictates different answers to those questions. So you're going to have different attack vectors with at layer 3 or level 2 versus level 1. You're going to have different indications. You're going to have different types of communications that are occurring, different devices that you need to understand and respond to in each of these layers. And I would largely say level 3 is like classically where the engineer workstation is. So this is where the engineers are programming the devices, the controllers are out in the field. The biggest challenge for an incident responder in that environment is understanding that software technology. It's basically industrial integrated development environment that they're writing code. It's not traditional code. It is using IEC code and ladder logic in order to program that device, but it's code. And you, from a forensics perspective, have to understand that at the application level. Same thing at the supervisory. It's still mostly Windows devices at that host, but the skill set that's lacking at the supervisory network is what is an energy management system really? What artifacts are on the server that can help me piece together a timeline? What artifacts are on a system operator's machine that I need to hone in on to understand if there was an impact, not within the host itself, but within the industrial process? So these are a breakdown of how you can approach that. And it's a struggle because the analyst, the responder, if it's their first time walking this environment, they're going to have a bad day because they don't have the pieces in order to do their job. We talked about hunting yesterday, and I think Dragos probably has a slightly different version of definition of hunting than a lot of what I heard yesterday, and I wanted to just kind of hone in on that a bit. So from a Dragos perspective, hunting is understanding that you have all these security controls. Apparently in banks you have 300 systems that are deployed out there doing stuff. And yet there's still this gap of visibility or control or defenses that you have because the adversary is always changing and kind of it's just kind of how the world exists. Defenders are always catching up, so there's this gap in your defenses. Hunting is focused in on that gap. So it's coming up with a hypothesis of we believe the adversary is performing an action here. We have no automated tool to actually detect that. So we're going to take the humans and apply humans to it. We're going to throw them out there, equip them with the right data, collect that data, and then hunt on that data. And then ideal circumstance is after the conclusion of that hunt, you've left some new piece of automation, such as orchestration, in place that is filling that gap so that you never have to do that hunt again. You can then move on to another interesting hypothesis challenge that's in your environment. This works really well inside of industrial control systems because, one, because that gap that I was talking about is really large. So you can make improvements very quickly without investing in capital projects that's going to take 2 or 3 years to deploy out there. You can instead fine-tune the environment, make it more defendable by doing hunts and automating at the end of each of those steps. Industrial control systems are also really finicky, and you don't want to necessarily do an action inside of an industrial control system environment that is going to be detrimental to that, right? And hunting is generally an extremely passive sort of process. So it fits very well whether you're in a maintenance cycle or if you're in production, you can still perform a hunt. You can still collect data off of devices. You can actively collect network traffic, all very passive, take it out of the environment, and then perform the hunt on that data set in a safe fashion. So in that regards, you can quickly gain an understanding of the environment through these hunt cycles. And then going back to that workforce gap of how do you train industrial responders to be able to handle themselves when they're not responding to intrusions on a daily basis inside of industrial environments. The exact same skill set that you're usually using on hunting applies to industrial response. So if you want to train someone to be a really good responder, have them hunting on a regular cycle, and it's going to build that skill set, that analytical skill set, that investigative technique, them understanding the tools, their environment, and how to apply it in usually pretty stressful situations. And also on the hunting side, I believe, and Dragos believes, and we've codified this in a lot of our software, that doing IOC sweeps is, you could say that that's like a hunt, but it's like the most basic version of a hunt. So there's been a lot of conversation on IOCs and how we create orchestration around that. That's awesome. Once you've done that, you still have a gap somewhere in your environment. You no longer maybe need to focus on a bunch of indicators that are being pumped out from somewhere, which is great, but you should then take that effort that you now have, that capability, that new time that you have each week to do hunts to further shrink that gap. So I would challenge you on not calling hunting like just and distilling it down to doing IOC sweeps. It's much broader than of thinking of a particular consequence that an adversary could have, and then figuring out how they would achieve that, and then going and looking for it. And moving it from a atomic indicator sort of perspective and leveling it up into understanding the behaviors that you would need to detect from an adversary and focusing on those behaviors instead, which I think goes very well in line with some of the adversary playbooks that Rick was talking earlier on. So with hunting and how you can kind of solve hunting inside of industrial environments and how Dragos focuses on this is framing it in a very intelligence-driven sort of perspective of creating visibility based on intelligence requirements and then identifying your collection sources and keep going through that loop over and over again. So one of the most challenging aspects within, I think, cybersecurity in general, not just industrial security, is understanding what the business needs. The business doesn't, if you ask a business owner, what are your worries about cybersecurity? How can I help you? It's a really broad question, and you're probably not going to get very good answers. But when you can start developing that relationship with that business owner, say VP of transmission, what assets are you most concerned about from a transmission perspective on if they were attacked. You go, oh, there, this one, and this one. And that then allows you to start honing in on, okay, well, I have these three substations. What is my visibility within those substations? How can I generate higher visibility on, say, a attack delivered from a control center into one of those substations? How can I detect that? And which leads to a collection plan that you then continually cycle through. The idea here is not a thought experiment of what do I need to go hunt for, but creating operationalizing this in a way that is reoccurring in your SOC, so that when your SOC gets a report from a government agency on a attack on industrial control systems, they can refer to something like this that tells them all of their data sources in those environments and where to hone in and focus on that from a collection. So that if it were an attack that happened 90 days ago, you can quickly say the best that we can do is 30 days of firewall logs. Everything else we don't have visibility on. That should cause a new conversation on your intelligence requirements gathering side from the business owner saying, hey, we need to up this to 90 days of collection across all of these devices. How do we do that? And that's that feedback loop that threat hunting can drive through this concept that we've stolen from the intelligence community, frankly, on collection management and what we call collection management framework or CMF. So that's how we approach it from a services perspective at Dragos on getting our customers up to a higher level of capability. But we also have response. So this is a little training kit that we use in our training class. And so I approached how do you do forensics on that? There's no keyboard. It's an embedded device. This is a Phoenix Contact, a PLC with a couple switches, and there's a dial there that controls the volume of water that's in the tank. If you give that to an incident responder, if you tell them there's a new variant of Trisis on here, I'm pretty sure, find it. What do you do? That is the current state of where we are inside of industrial control systems. But we're in a good state because it's mostly training and capabilities growth at that point. A little bit on technology, for sure. But that user manual there shows 80% of what the forensics person needs to approach. For instance, it explains the state of the PLC with the run and program, which is really important to the device. It defines all of the I/O and where all the I/O is. It explains there's an SD card that holds configuration information. That's extremely helpful for a forensics person who's trying to generate a timeline, right? You would not identify that there's an SD card on here because it's on a DIN rail there. So the SD card is on the side right here. You would not see that out in the field, which, by the way, if you're out in the field, it would be covered in dirt and muck and everything. So you definitely wouldn't see just a little SD card on the side there. You can kind of see the slot right there. There's the SD card slot. So you can start, and so a forensics person approaching control system or approaching a Windows box, they instinctively ask a lot of questions. They instinctively record the IP address, the MAC address, the host name, all this other information. They don't necessarily have it codified in their playbooks, in their procedures on how to do that for a controller. They don't understand to ask, this is an embedded device, what OS is it running? Oh, it's running a Phoenix Contact OS called, I think it's called Phoenix OS, which is a derivative of Linux. It's just sitting on top of Linux. Okay, well, that's very helpful. What interfaces exist? Does it have how many network interfaces does it have? In this case, it has 2. can you program or what are the capabilities that you can interface with that network card, and how are they different from the console port there? So if I plug in serially, does that offer new capabilities versus talking to it over the network? We talked about removable storage. What's on the storage? What kind of file system is it using? And how can you extract that out and understand timestamps and the data that's resident on there? These are the questions. Basically, the application level of the industrial process is what is unknown to the forensics person. The engineer that's programming this knows all of that information. He just doesn't like or doesn't know the incident responder. So you have that gap in capability, which goes to that whole IT-OT divide that I referred to earlier. And then you have at the network level. When a forensics person hooks up to that device and sends a program over and changes the ladder logic, if they're sniffing that network traffic, they're going to see this bunch of binary. And they're going, I don't know what that is. But there's ways of approaching it, even for a forensics person that doesn't know anything about that protocol. These protocols are usually pretty simple. They're generally serial-based, or they're generally binary-based because they're coming from a serial world. And so it becomes easy for a forensics person who has access to the engineering software to click a button and see what traffic gets generated, save that traffic off, click another button, see what gets generated, and then do a diff there and explain, these two values changed over here. This one keeps incrementing, and maybe it's kind of a counter, and start developing an understanding of the protocol and understand, instead of a line of binary, what the message type is, what command is being sent. These are very helpful on the protocol side for an incident responder to understand what's going on in that environment, right? This can be operationalized by constantly having software deployed out in systems, which is definitely where the focus, I would say, with a lot of the asset owners and the market itself is focused on passive collection. I think a segment of the vendors out there focused on anomaly detection and running a machine learning algorithm on a really small data set and then finding a bunch of anomalies and outliers and alerting on that. Dragos does something similar, except we do those behaviors, those threat behaviors I talked about before, rather than to provide context. So instead of a bunch of anomalies being detected with no context to it on if it's good or bad, we're then linking that intel component on top and explaining that this is, say, lateral movement inside the environment or some sort of other nefarious activity. So with that, I had like earlier Rick talked about the Cyber Threat Alliance and overviewed what that does. He mentioned that there'd be a press release tomorrow on 4 new companies. Dragos is actually one of those companies, so we're excited to be part of the Cyber Threat Alliance, which I'm happy the timing worked out and I could announce it here. We also have another announcement that went out today as well, and this is more on the information sharing aspect. We received a grant from DOE on a program that we called Neighborhood Keeper. So the tagline of Dragos is very grandiose. It's safeguarding civilization. We believe in that very firmly. What that means to us is it's not safeguarding the biggest companies that have industrial control systems. It's safeguarding everyone. The Neighborhood Keeper program is, in essence, us finding a way to approach all the municipalities, the co-ops, the smaller utilities that don't even have a security person. They might have an IT person, but they may have also outsourced that because the entire company is 50 people. And they're serving water or utilities across a long range, along with other co-ops in a very rural sort of session. They don't have anything defending them. They don't have the capability or technology to deploy out there to understand it. That Neighborhood Keeper program is, in essence, deploying out technology to those co-ops to understand what's happening, not on their internet perimeter, but what's happening inside of their OT environment in an aggregated form, and generating a feedback loop of getting that information back out to them that's actually actionable to somebody who is not a cybersecurity professional by trade. So Dragos doesn't have a lot of play in the information sharing space directly, but we're very excited by the Neighborhood Keeper program because we're trying to find that model of not just what works for, say, the top 10 banks of the world, but how do we influence the technology? How do we change that practical or the common Purdue model of level 1 through 3 as one cohesive thing, and influence it at that smaller co-op level where they can start applying good architecture practices, and that's what we're pursuing with the Neighborhood Keeper program. Thank you for your time. I appreciate it.